Good day, everyone, especially to our beloved and most handsome instructor, Engineer Renante Siurang. This is a continuation of the Chapter 15 reports, which is the Water Waste and Disposal System. By the way, I'm Richard B. Escoobilla, your presenter for today. My topic is all about on-site individual sewage treatment. That was found in Chapter 15.3. We are going to discuss the 5 subtopics on this chapter, or the OSST system, which is the on-site sewage treatment, primary treatment equipment, the high-level alarms, secondary treatment and disposal equipment, and the last one is the general regulation. First is the on-site sewage treatment. On-site sewage treatment, or the OSST system, traditionally called septic systems, usually consist of building sewer, which lead from the building into a septic tank, then into a distribution box that feeds the fluid or effluent into a drainage field or disposal field. Let's see these figures from your home into the septic tank, then from septic tank into the distribution box. On-site or decentralized wastewater treatment system are used to treat wastewater from a home or businesses and return treated wastewater back into the receiving environment. They are typically referred to as septic systems because most involve a septic tank for partial treatment. And OSST system consists of primary treatment components such as septic tank and a disposal component, which is typically a drainage field. Household and human waste flows in a pipe from the building sanitary drainage system to a septic tank. Inside the septic tank, anaerobic and aerobic bacteria converted the waste into minerals, gases, and a liquid waste called the effluent. The result of the aerobic and anaerobic bacteria is the effluent. Aerobic and anaerobics is with or without the presence of air. Clarified effluent leaves the septic tank and flows in a pipe to a drainage field. If the drainage field's piping is higher in elevation than the septic tank outlet, a pump tank and pump are required. The effluent is distributed as evenly as possible throughout the drainage field where it percolates through the soil. Gravity is typically the driving force behind wastewater and effluent flow. Second is the primary treatment equipment. Wastewater from building is first treated in primary treatment equipment such as tanks or filters. In the primary treatment process, anaerobic digestion and settlement of solids is wastewater takes place. Primary treatment removes materials that will either float or readily settle out by gravity. It includes the physical processes of screening, comminutions, grit removal, and sedimentations. As we can see in this figure, no rose wedge. So ang first na steps nito, process of screening. So sa laon sang screen yung para ma-block yung mga dagko nga kwan, like for example woods and rugs and bulky objects that can clog pipes para hindi masampungan ang mga tubo nga nagod. Pagkasunod ang comminutor. Ang katong mga last tong wala nasala sang screen, syempre mga dagko lang iya masala, na siya i-grind sang comminutor para magagmay iya nga dugmokon. Pagkatapos sa grit chamber. So maglugdang tong mga Itong mga good, itong nasala, itong gidugmok sa community maglubdang siya nga na siya dahil. Types of primary treatment equipment used in OSST system include the following. First is the septic tank. Septic tank is a watertight covered container designed out to settle out and hold solid waste and partially treat water with beneficial bacteria. It represents a relatively low cost, low maintenance method for primary treatment of wastewater. Septic tanks are constructed of concrete, metal, fiberglass, or plastics and are commonly placed underground with a top surface covered with grass. A septic tank can be thought of as a separating device. It allows heavier solids to settle to the bottom of the tank and lighter particles such as grease and soap float to the top of the tank. The lighter particles form a layer known as the scum. Aerobic and anaerobic bacteria digest up to 50% of the wastewater solids that enter the septic tank. The remaining solids accumulate as sludge in the bottom of the tank. The bacteria require at least 24 hours for proper digestions of solids. The greater the surface area of the liquid in the tank, the more solids that bacteria can digest, thus improving the clarity or quality of effluent discharge to the drainage belts. So no pag mas dako ang surface area sa aton nga tangke, mas makadigest ang aton bacteria sa mga solids para ma-info pang iyang clarity quality sa para mapagwa nga effluent sa aton nga septic tank. There are some examples of septic tank: a precast concrete septic tank, so on, and the galleon, polyethylene plastic septic tanks, so on and so forth. Second is the aerobic tank. Aerobic tanks are substitute for a septic tank. They are consist of a thrust tank, an aerobic chamber, and a settling chamber. Some systems require a thrust tank to be installed external to in front of the unit. Pre-manufactured aerobic tanks use wastewater treatment processes similar to the municipal wastewater treatment processes. The clarified effluent is usually discharged into a drainage field. Aerobic tanks works more effective than septic tank and thus can be smaller in size. So mas effective ang aerobic tank tapos mas smaller size siya kaysa sa septic tanks. This is an example of aerobic treatment. Number 3 is the pump tank. A pump tank is a watertight container used to temporarily store clarified effluent before it flows into a drainage field. Wastewater is first treated in an aerobic or septic tank. The effluent then flows by gravity into the pump tank. When the level of stored effluent reaches a present elevation, a float switch turns on the pump. The pump discharges the effluent to the drainage field several times a day. Excess effluent produced during periods of high generations of water can be stored in the pump tank temporarily and then discharged in the drainage field during low generation period. A remote alarm sounds if the effluent level in the tank becomes too high. Pump tank materials are typically concrete, plastic, or fiberglass or polyethylene. Tanks are also used. This is an example of pump tank. Number 4 is the sand filters. A sand filters is a lined impermeable container containing a bed of granular materials that provides additional treatment of effluent such as it flows from the primary treatment tank to the drainage field. They are usually placed underground with a top surface covered with glass at sites that have near surface bedrock or high water table. Sand fillers are usually constructed with above ground concrete walls. There are two types of sand failures, the intermittent sand failures and recirculating intermittent sand failures. Intermittent sand failures, the effluent is dispersed throughout the upper portion of the granular bed through the perforated pipes. The effluent then flows by gravity through the granular materials until it reaches another series of perforated pipes where it flows to a pump tank. While a recirculating intermittent sand filler requires a recirculating pump tank, the pump is used to mix filtrate with incoming septic tank effluent. The effluent is circulated several times through the sand filler filter media before it pumped to the drainage field. Number 5 is the trash or grease tank. A trash tank is occasionally used in conjunction with anaerobic tank. The trash that tanks removes materials that treatment microorganisms are unable to degrade. Several types of aerobic tanks used for small wastewater flows have the trash tank enclosed inside the unit. Grease tanks are used with septic and aerobic tanks, usually in commercial application. Next is the cesspool. A cesspool is covered underground container that receives untreated sewage directly from a building and discharged into the soil. Opening in the cesspool walls allows untreated sewage to pass through and seep into the surrounding soil because of the health concerns tied to the discharge of raw sewage. Use of cesspool is considered unacceptable today in most applications in developed countries. This is an example of cross-sectional of cesspool. Next is the high-level alarms. A high-level alarms is used to alert the homeowner or building operators of liquid inside the tank reaches a level that is higher than it would be if the pump were operating normally, or if the liquid inflow is greater than the maximum pumping capacity of the pump. High-level alarms are used in sump, sewage, or effluent installations. These alarms can either be purchased separately or as part of the pre-assembled package. A device installed in a fuel storage tank that is capable of sounding an alarm during the filling operations when the liquid level nears to the top of the tank. This is an example of high-level alarm. So, ina-install niya siya sa aton nga mga tank no sa sulod sang tangke. Tapos pag ma-reach na sang sang water ang sa maximum level na siya, so mag-alarm ni siya para mabalance ang owner ta kung puno na ang tangke. Nga na. Secondary treatment and disposal equipment. A drainage field provides a secondary treatment and is the final disposal locations for clarified effluent from wastewater. A piping network carries effluent from a septic tank or pump tank to the drainage field for further treatment within the soil or disbursement into the air. Secondary treatment is the removal of biodegradable organic matter from sewage or similar kinds of wastewater. The aim is to achieve a certain degree of effluent quality in a sewage treatment plant suitable for the intended disposal option. This is achieved with the physical phase separation to remove soluble solids, followed by biological process to remove dissolved and suspended organic compounds. Secondary treatment is portion of the sewage treatment sequence, removing dissolved and colloidal compounds measured as biochemical oxygen demand or BOD. This is an example of secondary treatment. After ng primary treatment, apply naman yung secondary treatment. Ganyan siya. Primary effluent. Types of drainage fields are described below. First is the absorption drainage field. An absorption drainage field is consists of rows called lines of underground pipes through which the clarified effluent passes. Perforated pipes are led in shallow underground beds or narrowly cut trenches filled with a gravel, then are typically covered with glass. So this is an example of conventional absorption field. So ano siya, no? Ng distributed box. Ano siya? A distribution box. Receive effluent from septic tank and distribute it to each individual lines that of the drainage field. The box is connected to the septic tank with a watertight sewer line, perforated pipe, frequently called drain tiles because they used to be made by clay tile pipe disperse the clarified effluent throughout the drainage. This is an example of distribution box. Yan siya. An absorption drainage trench is an absorption field that consists of one or more individual trenches containing the drainage pipes. Trenches typically have a maximum width of 3 feet with a minimum 6 feet between trenches. An absorption drainage bed is an open drainage field without trenches containing a drainage pipe. A drainage field is take any of a number of shapes depending on the contours of the ground, the size of the lot, and the location of any well or stream on the property. Ano siya? Next is the gravelless drain fields. A gravelless drain field distributed effluent into the soils through gravelless drain pipe instead of gravel. As a result, these systems are also called the gravel or no-rock drain field system. Like an conventional on-site sewage treatment system, gravelless pipe requires only a septic tank to treat the wastewater. These pipes takes many forms including the jet, textile fabric wrap, pipe and open bottom chamber, fabric wrap, drain fields use proprietary large corrugated and perforated polyethylene tubing cover the permeable nylon, geotextile filters like fabric and distribute water around the pipe. The third one is the evaporation bed or trench drainage field. An evaporation bed or evaporation trench drainage field treats wastewater by evaporating the water from the soil and by transpiring the water into the air through plants and grasses. Vegetations cover the soil, prosper on the nutrients introduced by effluent. An evapor, eva, evapotranspiration drainage field typically consists of two sets of perforated drainage pipes and gravel, soil lining if needed, and topsoil backfill for vegetation growth. The surface area of the evapotranspiration drainage field is divided into two bed sections by periodically alternating flow to sections of bed. The other sections of bed is periodically rested. So this is an example of evapotranspiration bed septic system. Fourth is the low pressure dosing drainage field. Low pressure dosing drainage fields typically consists of narrowly cut 6 to 12 in wide trenches containing small diameter PVC dispersion pipes. Low pressure dosing system also include a pump tank and an electrical control system. As effluent flows from the septic tank into the pump tank, the water level rises inside the tank. When the fixed water level reaches the pump tank introduces the water into water drainage field. In the drainage field, the effluent is introduced into the drainage field through small holes in the drainage pipe. The soil provides additional wastewater treatment, soil particles filter the effluent and microbes in the soil, kill the bacteria and pathogens. Pump effluent low pressure dosing drainage fields are basic LPD trench system intended for single-family homes and cannot be used for commercial or institutional facilities. They consist of septic tank, pump tank, and drainage field. So this system is capable only for single family at dili siya capable for commercial or institutional facilities. Next is the absorption mount. Absorption mount is consists of septic tanks, a pump tank, effluent pump, and controls an above grade drainage system. The drainage system consists of perforated drainage pipe leads in a deep layer sand and sandy loam soil that is placed above the natural soils. Mounds are used in sites that have shallow soils. They typically require a minimum depth of 12 inches of natural soil to a limiting layer such as bedrock or high water table. Natural surface slopes greater than 10%, 10 feet vertically rise and 100 feet vertically run are any suitable for absorption mounds. For slowly permeable clay and clay loam soils, a loading rate of from 0.20 to 0.25 gallons per day per square foot is usually satisfactory. This typically means that a large drainage area is required for absorption mounds, which can be substantially increase land area requirements for these types of drainage field system. Number 6 is the spray distribution. Spray distribution system spray the disinfected effluent into the ground surface in a manner similar to a lawn irrigation system. This required an advanced treatment process that purifies the water, a pathogen removing disinfecting system, a pump tank, a distribution pipe, a disposal area containing the spray heads. Next is the leaching chamber drainage field. Leaching chambers are proprietary, commercially produced plastic chambers pre-molded into the dome shape. They can be easily assembled and placed in trenches. Depending on the site condition, leaching chamber drainage fields can require less and land area than other conventional absorption drainage fields. Leaching chamber distributed effluent to the soil in manner similar to conventional gravel field trench system. Each chamber dome supports the soil above it while maintaining sufficient volume inside the effluent storage. Next is the subsurface drip drainage field. Subsurface drip system consists of a septic tank, a pump tank, a filtering device, and a drip distribution system. An aerobic tank is typically used for the primary treatment process. When a septic tank is used, additional treatment as sand filters is required. Treated wastewater pump through a filtering device that removes larger particles to reduce clogging of the drip emitters. The filtered effluent is distributed to a tubing leg just below the ground surface. Subsurface drip system can be installed on step slopes and at sites containing dense clay soil and soils overlaying shallow bedrock. Number 9 is the seepage pit. A seepage pit is a deep underground container that receives clarified effluent from a septic tank. It has opening in its walls that allows effluent to pass through and seep into the surrounding soil. A seepage pit function like absorption drainage field except that effluent seeps through opening in the side wall of the pit rather than through the bottom of the trench or bed. A seepage pit tends to be deeper than an absorption bed or trench. It is designed on the basis of the sidewall area. It can serve as an alternative to a drainage field, but only when surrounding soil has a good percolation rate, usually below 30 mean or inch, and the water table is very deep. Last is the general regulations. Typically, an OSST system or on-site sewage treatment system should not be installed, repaired, or rehabilitated when a community sanitary sewer system is available or where a local ordinance requires connections to a community system. An OSS system is generally not permitted when building site is located within 200 feet from a community sewer. When a community sanitary sewer become available within 200 feet, any building then served by an OSS system should connect to the community sanitary system sewer within a time frame or under condition set by the governmental authority. Generally, it is illegal to discharge any wastewater from OSST system except under a governmental permit. To any ditch, streams, ponds, or lake waterways or drain tile or to the surface of the ground in older buildings, existing systems having any of these prohibited discharges are typically required to eliminate these discharges by constructing a system in compliance with current requirements. My next topic is all about the testing of soil and water for drainage that was located chapter 15.4. First is the soil evaluation. Soil evaluation. So, bago ta mag-install or mag-build sa isa ka septic tank mo, kailangan nato i-test ang first step naman always pag may mga projects tayo, kailangan natin i-test yung capacity ng ating soil. So soil evaluations is an important part of on-site sewage system because it treats and disposes of septic tank effluent soil from drainage. Soil for a drainage field must effective filter effluent and not allow inhibiting consolidation of swelling of the soil. For example, dense clay soils do not absorb or filter the effluent properly and are considered an acceptable soil for OSST system with an absorption drainage field. A soil evaluation is an assessment of subsurface soils condition at a specific site that is conducted under the supervision of a professional engineer or professional geologist. Consideration is given to the effluent of the following. First is the topography, drainage ways, terrace, floodplain, percentage of land slope, locations of property lines, locations of easement, buried utilities, existing and proposed tiles, lines, existing proposed and abandoned water wells, amount of available area for the installations of the system, evidence of unstable ground alterations, cutting, filling, compacting of existing soil profile, and soil factors determined from a soil analysis, percolation test, and soil surveys map of if available. Soil percolation test. A soil percolation test is a subsurface soil test at a depth of a proposed absorption system to determine the water absorption capacity of the soil. The test identifies the soil percolation rate, the rate that water seeps through saturated soil. This is an example of field measurement for percolation rate. So, kailangan natin siya ng measuring stick, reference stick, para naman siya. Measure drop per R. Percolation testing procedures are established by government health entity, commonly municipal, country, or state office of health. Number one is the number and location. 6 or more tests shall be made in separate test halls spaced uniformly over the proposed absorption area site. Second is the result. Percolation holes located within the proposed absorption area shall be used in the calculations of the arithmetic average percolation rate. Type of hole. Number 3 is type of hole. Holes having uniform diameter of 6 to 10 inches shall be bored or drag as follows. Number 4 is the preparation. Number 5 is the procedure for pre-soaking, and there are two conditions of soil according to the following procedures. The initial pre-soak, hole shall be filled with water to a minimum depth of 12 inches over the gravel and allowed to stand undisturbed for 8 to 24 hours prior to the percolation test. Letter B is the final pre-soak. Immediate before the percolation test, water shall be placed in the hole to a minimum depth of 6 inches over the gravel and readjust every 30 minutes for 1 hour. Number 6 is the determination of measurement interval. The drop in the water level during the last 30 minutes of the final pre-soaking period shall be applied to the following standard and determine the time interval within readings each of the percolation hole. Number 7 is the measurement. After the final pre-soaking period, water in the hole shall again be adjusted to approximately 6 inches over the gravel and readjusted when necessary after each reading. Next is the BAD test. The BAD test measures the amount of dissolved oxygen organisms are likely to need a discharge wastewater. The test is important for evaluating both how much treatment wastewater is likely to require, the potential effect it can have on receiving water. To perform the test, wastewater samples are placed in the BOD bottles and are diluted with specially prepared water containing dissolved oxygen. The dilution water is also seeded with bacteria when treated wastewater is being tested. The amount of dissolved oxygen is diluted samples is measured and samples are then stored at a constant temperature of 68 degrees Fahrenheit or 20 degrees Celsius. Commonly, incubation periods are 5, 7, or 20 days, with 5 days or BAD 5 the most common. At the end of the incubation period, the dissolved oxygen is measured again. The amount was used expressed in milligram per liter is an indication of wastewater strength. Coliform, next is the coliform test. The coliform test determines whether wastewater have been adequate treated and whether water quality is suitable for drinking and recreation. Because they are very abundant in human waste, coliform bacteria are much easier to locate and identify in wastewater than viruses and other pathogens that cause severe diseases. Therefore, coliform bacteria are used in indicator organisms for the presence of other more serious pathogen. Some coliform are found in the soil, so tests for fecal coliform are considered the most reliable. However, tests for both total coliform and fecal coliform are commonly used. This is an example of total coliform indicator. So pag yellow siya, so positive siya. Pag nag-remain siya sang pula, negative test. Pag sa yellow, so may presence siya, may hara siya sang coliform na bacteria. Pero pag mag-remain sa red, ano siya, wala siya sang coliform. So pwede siya inumin, pwede siya suitable for drinking or creation siya pag mag-remain red yung bottle na sa test natin. Pero pag naging yellow siya, hindi siya pwedeng inumin. There are two methods of determining the presence of density of coliform bacteria. First is the membrane filter technique provides a direct count of colonies trapped and then cultured. Ang first nga methods ang membrane filter. So siya, i-trap siya kung ito siya first, untreated water. So after siya matreat, so masalang yung mga higko, mga sapat-sapat, unwanted falling layer, mga unwanted organisms. Ito na siya ang result ng disinfected water pagkatapos siya na test na sala. Second is the multiple tube fermentation method provides an estimate of most probable number or MPN per 100 milliliters from the number of test tubes in which gas bubbles for after incubation. Ayan siya i-test. 3 positive, 1 positive, and 0 positive. So, ganyan siya. And that's all for my report. Thank you for watching. Thanks for watching. Keep safe, everyone.